Every mass extinction in Earth's history killed most life without killing all life. The asteroid that ended the non-avian dinosaurs, the volcanic catastrophes of the Permian extinction, even the worst biological crises left survivors hidden in deep oceans, hydrothermal vents and kilometers of rock beneath the surface. Life endured because the killing mechanisms never reached every refuge simultaneously. To truly end all life requires crossing a far higher threshold. It means delivering lethal conditions, not just to forests and oceans, but to bacteria 5 kilometers underground and microbes living at the thermal limits of biology. When examined in physical terms, only a small number of known mechanisms can plausibly achieve that outcome. Some operate with terrifying speed. A sufficiently large impact can transform the planet's surface into a global furnace within roughly 2 hours. The question is not what can cause extinction, it is what can leave nothing behind, what survival actually requires. Before any specific extinction scenario can be evaluated for its capacity to end all life, rather than merely most life, it is necessary to understand what life actually requires to persist, how distributed it is, how chemically diverse it is, and why the organisms most likely to survive any given catastrophe are not the ones most people think of when they imagine survivors. Life on Earth is not primarily surface life. The visible biosphere, the forests, the grasslands, the coral reefs, the familiar animals and plants that constitute the living world, as most people understand it, is a thin film on the outer surface of a planet that extends tens of kilometers deep in every direction. Beneath that surface, the rock is not lifeless. It is populated by organisms that have been living in conditions of extreme pressure, extreme darkness, extreme heat, and near total nutrient deprivation for billions of years. The deep subsurface biosphere, as it is called, was not seriously investigated until the late 20th century, and what has been found there has consistently surprised the researchers who found it. Bacteria and archaea have been recovered from depths exceeding 5 kilometers in continental crust, living in rock pores and fractures at temperatures between 60 and 120 degrees Celsius. Pressures orders of magnitude above the surface, and with access to energy sources derived from the chemical reactions between water and rock, rather than from sunlight. These organisms metabolize so slowly that individual cells may divide once every few thousand years. A single bacterium in those conditions is not living fast or burning bright. It is persisting, extracting the minimum energy required to maintain its molecular integrity from a chemical environment that would be lethal to anything evolved for the surface. Their very slowness is a survival mechanism. They are essentially inert relative to surface standards, waiting out conditions that would be temporary on geological timescales and expanding when conditions improve. The total biomass of this deep biosphere is genuinely uncertain. Some estimates place it as comparable to the total biomass of all surface life combined, suggesting that by sheer mass, there is as much life beneath our feet as there is above them. Whether that estimate is accurate or an overestimate by a factor of several, the qualitative conclusion is robust. A very large amount of life exists in places that are thermally insulated from surface events, physically shielded from radiation, chemically buffered from atmospheric changes, and essentially disconnected from the surface food web that catastrophic events typically collapse. Hydrothermal vent communities represent a second major category of potential survivors. At the mid-ocean ridges, where tectonic plates separate, seawater percolates down through the fractured crust, heats to several hundred degrees Celsius in contact with the underlying magma, and erupts back through the seafloor in what are called hydrothermal vents. The water emerging from these vents carries dissolved sulfur compounds and metals that provide the chemical energy for entire ecosystems built on chemosynthesis rather than photosynthesis. The organisms at these vents have no dependence on sunlight, no dependence on the surface atmosphere, and no dependence on any food chain connected to the surface world. Above them sit kilometers of ocean, an insulator against radiation and thermal pulses from above. Below them is the geological heat engine of the planet itself, which will continue operating regardless of what happens at the surface. Understanding these two categories of life, deep rock organisms and hydrothermal vent communities, is essential for understanding what total sterilization actually requires. Any event that kills only surface life is not total sterilization. It is a mass extinction, potentially catastrophic, potentially civilization ending, but not the end of life itself. To achieve actual total sterilization requires heating the entire planet, including the rock 5 kilometers deep and the water at the bottom of the ocean, to temperatures exceeding the survival threshold of the most heat-tolerant known organisms, which is approximately 130 degrees Celsius. Maintaining those temperatures long enough that organisms cannot survive by metabolic shutdown or spore dormancy is an additional requirement. This is a substantially higher bar than killing everything on the surface, and it is the bar against which every proposed extinction mechanism must be evaluated. The ocean vaporizing impact, the physics of total erasure. The asteroid impact that ended the Cretaceous period 66 million years ago was approximately 10 to 15 kilometers in diameter. It traveled at roughly 20 kilometers per second. The energy it released was equivalent to approximately 100 teratons of TNT, roughly 2 million times the yield of the largest nuclear weapon ever detonated. It killed approximately 75% of all species. It did not end all life. Understanding why it did not and what would be required to cross that threshold requires working through the specific physics of what happens when objects of different sizes impact a planet. The Chicxulub impactor, for all its destructive power, was not large enough to deliver lethal conditions to the deep biosphere. The surface heating it produced was intense but brief. The ejector re-entering the atmosphere heated the upper atmosphere globally and produced a thermal pulse at the surface, intense enough to ignite forests simultaneously across hemispheres. But this thermal pulse lasted on the order of hours to days at its most intense, declining as the ejector dispersed and the atmosphere cooled. The subsequent impact winter, driven by soot from global wildfires and sulfur dioxide from vaporized rock, was far more lethal to surface life over the following months and years. But it was a cold event, not a hot one. The deep subsurface warmed slowly, if at all, through this period, insulated by kilometers of rock and ocean above it. The threshold for ocean vaporization, the point at which an impact is large enough to convert the entire ocean to steam, requires an impactor of approximately 500 kilometers in diameter, traveling at typical impact velocities. An object 500 kilometers across is roughly 2/3 the size of Ceres, the largest body in the asteroid belt, which has a diameter of approximately 940 kilometers. The energy released by a 500 kilometer impactor at 20 kilometers per second is approximately 3 times 10 to the power of 30 joules. To put this in terms of something physically meaningful, the Sun radiates approximately 3.8 times 10 to the power of 26 joules per second. The impact would release energy equivalent to the Sun's total output over roughly 2 hours. That quantity of energy, deposited at a single point on Earth's surface, would produce effects qualitatively different from anything in Earth's recorded geological history. In the first seconds of the impact, the projectile would not slow down as it entered the atmosphere. Moving at 20 kilometers per second, it would punch through the atmosphere as though it were not there, compressing the air beneath it so violently that temperatures in the compression zone would exceed 50,000 Kelvin, roughly 9 times the temperature of the Sun's surface. The impact site would vaporize. The rock and the impactor would both become plasma. A crater several hundred kilometers across would be carved in the crust in seconds. The ejector column from this impact would not behave like the Chicxulub ejector column. It would not merely loft material into the stratosphere and upper atmosphere. It would blast enormous quantities of vaporized rock through the atmosphere entirely, into space, and back again as re-entry material globally. The quantity of material would be sufficient to heat the upper atmosphere globally, to temperatures that radiate lethal heat downward to the surface for hours, not minutes. Within the first 30 minutes of the impact, the global surface temperature would begin climbing. Not from the impact site, which is on one side of the planet, but from the globally distributed re-entry heating. The sky would become luminous as heated particles re-entered the atmosphere everywhere simultaneously. Within 1 hour of impact, surface temperatures would be climbing through 50 degrees Celsius globally. Within 2 hours, they would be approaching 100 degrees and continuing to rise. But the critical distinction between this event and the Chicxulub impact is what happens next. The energy deposited at the impact site does not simply disperse into space. A significant fraction of it heats the crust and the ocean. At the impact site, the crust is vaporized. Moving outward from the impact site, the rock is melted. Moving farther, it is heated to temperatures incompatible with any life. And the ocean at the impact site is entirely vaporized, launching enormous quantities of superheated steam into the atmosphere. Steam is a greenhouse gas. The partial pressure of water vapor in the atmosphere determines how efficiently the atmosphere traps heat. When the ocean at the impact site vaporizes, the steam does not immediately disperse and cool. It joins an atmosphere already heated by ejecta re-entry. The combination of heated atmosphere and the greenhouse effect of steam prevents the surface from cooling. The ocean, rather than acting as a thermal buffer that absorbs the energy and moderates the surface temperature, begins to evaporate globally as the sea surface temperature climbs. More evaporation means more water vapor in the atmosphere. More water vapor means more greenhouse warming. More greenhouse warming means more evaporation. This feedback loop, once started by an impact of sufficient energy, does not stop. The ocean does not fully evaporate in 2 hours. It takes much longer than that. But the conditions incompatible with surface life are established within 2 hours. By the time 2 hours have elapsed since the impact, the global surface temperature has crossed the threshold above which no known surface organism can survive. The deep subsurface is still cooler than the surface at this point. The rock is an effective thermal insulator on short timescales, but the surface heating is now self-sustaining. The feedback has begun. What started in 2 hours will continue for 1 million years until the ocean is fully evaporated and the surface temperature stabilizes at a new equilibrium incompatible with any known biology. The late heavy bombardment period, approximately 3.9 billion years ago, was a sustained episode during which the inner solar system was bombarded by a much higher flux of large impactors than the present rate. Some of the objects in that bombardment were large enough to have crossed the ocean vaporization threshold. Some researchers believe the early evolution of life may have been frustrated multiple times during this period, with life evolving and being largely destroyed by ocean vaporizing impacts, only to re-evolve from whatever survived in the deepest refugia during the cooling phase between impacts. Whether this scenario is correct cannot be definitively established from current geological evidence, since the geological record from that period is almost entirely recycled by subsequent plate tectonic activity. But the physics is unambiguous. Such impacts occurred. The question is only whether they crossed the threshold completely or left survivors. The gamma-ray burst, sterilization at the speed of light. A gamma-ray burst is the most energetic electromagnetic event known to occur in the universe. When a massive star exhausts its fuel and its core collapses to form a neutron star or black hole, or when two neutron stars merge, the energy released in a matter of seconds to minutes exceeds the total energy output of the Sun over its entire 10 billion year lifespan. Most of this energy is channeled into two narrow jets of gamma radiation, moving at 99.9% of the speed of light, one jet from each pole of the collapsing system, each jet subtending only a few degrees of sky. From the perspective of Earth, the critical geometry is whether one of those jets is aimed at us. If the jet is not aimed at us, A gamma ray burst thousands of light years away is visible as a brief flash of gamma radiation, followed by an optical afterglow. Scientifically interesting, but biologically irrelevant at Earth's surface. If the jet is aimed at us, the situation is categorically different. The first thing to understand about a gamma ray burst threat is that there is no warning. Gamma rays travel at the speed of light. The burst itself also travels at the speed of light. There is no precursor signal that can outrun the radiation. The star that produces the burst does not begin behaving unusually in any way that is detectable from Earth in the hours before the collapse. The collapse itself takes a fraction of a second. The jet emerges within seconds of the collapse. The radiation arrives at Earth simultaneously with any optical indication that the burst has occurred. From a practical standpoint, the burst and the arrival at Earth are instantaneous from any Earth-based detection system. The gamma radiation that arrives at Earth from a burst within the lethal range, estimated at approximately 6,000 to 8,000 light-years, for a burst of typical energy output directed at Earth, would immediately begin ionizing the upper atmosphere. Within seconds of arrival, the gamma photons, each carrying thousands to millions of times the energy of a visible light photon, would strip electrons from atmospheric molecules across the stratosphere and mesosphere globally. These energized electrons would collide with nitrogen and oxygen molecules, triggering a cascade of photochemical reactions. The most damaging of these reactions is the production of nitric oxide in enormous quantities. Nitric oxide reacts with ozone, breaking it down into molecular oxygen and nitrogen dioxide. Normally, the ozone layer maintains a stable concentration through a balance of production by ultraviolet photolysis of oxygen and destruction by various natural catalytic cycles. A gamma ray burst directed at Earth would massively accelerate the destruction side of this balance, depleting the global ozone layer within minutes. The ozone layer absorbs ultraviolet radiation from the Sun in the wavelength range of 200 to 320 nanometers, what is called ultraviolet B and C radiation. This radiation is directly damaging to the molecular machinery of life. It breaks chemical bonds in DNA, producing thymine dimers and other lesions that, if not repaired, cause mutations, cell death, or cancer in organisms with sophisticated DNA repair mechanisms, and simply kill organisms without those mechanisms. Without the ozone layer, the ultraviolet B flux at Earth's surface would increase by factors ranging from several to several hundred, depending on the completeness of the ozone depletion. The ozone depletion from a gamma ray burst would not be uniform or instantaneous in its biological effects. The depletion would be global, occurring simultaneously across the entire sunlit hemisphere of Earth that is facing the burst direction, and propagating to the night side hemisphere over the following hours as the atmosphere continues reacting. The biological effects would develop over hours to days, not in the first 2 minutes. Within the first 2 hours after a gamma ray burst from within the lethal range, the primary physical process is atmospheric ionization and the initiation of ozone depletion chemistry. The surface itself is not directly heated by the gamma radiation, which is largely absorbed in the upper atmosphere. The killing mechanism operates through the secondary effect of ultraviolet exposure after the ozone shield is compromised. Phytoplankton, the microscopic photosynthetic organisms in the sunlit surface layer of the ocean, would be among the first organisms to experience lethal effects as the ultraviolet flux increased over the hours and days following the burst. Phytoplankton account for approximately half of all photosynthesis on Earth and form the base of the marine food web. Their sensitivity to ultraviolet B radiation is well documented. At sufficiently elevated ultraviolet B levels, phytoplankton DNA sustains damage faster than the organism's repair mechanisms can address it. Growth rates drop, photosynthesis efficiency decreases, and eventually the organisms begin dying in large numbers. The cascade upward through the food web from phytoplankton loss would take weeks to months to complete. The direct surface lethality from elevated ultraviolet B would depend strongly on the completeness of ozone depletion and the depth of water or soil available to provide shielding. The surface waters of the ocean would offer limited but meaningful shielding, with ultraviolet B intensity dropping by a factor of roughly 10 per metre of water depth. Organisms living below approximately 10 metres of water would experience a dramatically reduced radiation dose compared to surface organisms. The critical question for total sterilisation is whether a gamma-ray burst can reach and kill the deep subsurface biosphere. The answer, under normal circumstances, is no. Gamma radiation from a burst at the lethal distance would be absorbed in the upper atmosphere, not at the surface. Ultraviolet radiation cannot penetrate kilometres of rock. The deep biosphere would be entirely unaffected by the primary radiation mechanism. A gamma ray burst from within the lethal range would therefore cause a catastrophic mass extinction at the surface and in surface waters without achieving total sterilisation. This is the same conclusion reached for the Chicxulub impact, but for different reasons. The two mechanisms operate through different physics, deliver their killing mechanisms over different timescales, and have different distributions of surviving life. The gamma-ray burst kills primarily through radiation and its atmospheric consequences, while leaving thermally insulated deep life untouched. The ocean vaporizing impact kills through heat, while leaving radiation-sensitive surface organisms equally dead. There is, however, a version of the gamma-ray burst scenario that approaches total sterilisation. A burst from within a few hundred light-years, close enough that the burst energy reaching Earth's surface is high enough to deliver a lethal radiation dose through any realistic shielding. At distances of 25 to 30 light-years, the surface dose from a burst pointed directly at Earth would likely be lethal to all surface life within hours of arrival. Whether such a close burst could penetrate to the deep subsurface depends on the specific energy spectrum of the burst and the absorption properties of rock. At the distances typically discussed, total sterilisation through radiation alone is not achieved. The deep biosphere survives. There are no known candidates within the lethal range for Earth at present. The nearest stars capable of producing gamma-ray bursts are hundreds to thousands of light-years away. Betelgeuse, at approximately 700 light-years, is a frequently discussed supernova candidate that will eventually produce an energetic explosion. But its jet geometry is not known to be directed toward Earth. And at 700 light-years, even a powerful burst would produce ozone depletion rather than direct surface sterilisation. The 2-hour sequence. To understand the 2-hour frame as a physical reality rather than a rhetorical device, it is necessary to trace the specific sequence of physical events in detail for the most relevant extinction mechanisms, noting what is happening minute by minute and why 2 hours represents a meaningful threshold. For the ocean vaporizing impact scenario, the sequence begins at the moment of impact. At 0 seconds, the impactor enters the atmosphere. At 20 kilometers per second, the atmosphere offers no meaningful resistance. The air beneath the projectile compresses to plasma temperatures. No warning has been issued. No seismic signal has reached any recording station. The impact occurs. At 1 second, the impactor has travelled approximately 20 kilometers through the atmosphere and reached the surface. The explosive release of energy begins. The crater begins to form. Vaporized rock and the vaporized impactor are blasted upward in an expanding column. At 10 seconds, the ejector column has reached the upper atmosphere. The crater diameter is several hundred kilometers. Everything within a radius of roughly 500 kilometers of the impact site has been vaporized, incinerated or crushed by the seismic shockwave propagating outward through the crust. At 1 minute, the ejector column has reached space. Material is being distributed globally on ballistic trajectories. The seismic wave generated by the impact is propagating through the crust at speeds of approximately 8 to 13 kilometers per second. It will take roughly 20 to 30 minutes to travel through the crust to the antipodal point on the opposite side of the planet. At 10 minutes, the ejector that was blasted into space begins returning to the atmosphere globally. Each piece of rock and debris, re-entering at orbital velocities, heats through aerodynamic friction as it decelerates. The upper atmosphere over the entire planet begins to glow. This is not visible light from the impact site, which is on one side of a spherical planet. It is the infrared and visible glow of heated re-entry material globally distributed across the sky. At 20 minutes, the seismic wave from the impact reaches the opposite side of the planet. Earthquakes of extraordinary magnitude occur globally as the seismic energy is released. Every structure ever built by human civilization collapses. Mountain ranges experience massive landslides. The ocean floor near the impact antipode is displaced, generating enormous tsunamis. The global surface temperature has begun rising measurably as the heated atmosphere begins radiating downward. At 30 minutes, the rate of ejector re-entry is at its peak. The sky globally is a continuous luminous display as particles decelerate in the upper atmosphere. The infrared radiation emitted by this heated layer is significant. Surface temperatures are climbing through levels compatible with but uncomfortable for surface life, approximately 40 to 50 degrees Celsius in most regions. Forests and grasslands have not yet ignited, but the conditions for ignition are approaching. At 60 minutes, surface temperatures have climbed above 60 degrees Celsius globally. This temperature is above the survival threshold for most multicellular organisms. Mammals and birds experience heat stress leading rapidly to organ failure. The ocean surface temperature is rising. Forests in the drier regions of the world are beginning to ignite as the radiant heat from above exceeds the ignition threshold for dry organic material. The sky is bright with re-entry heating and beginning to darken as smoke from fires adds to the aerosol loading. At 90 minutes, surface temperatures are approaching 80 to 100 degrees Celsius globally. All surface life is dying or dead. The ocean surface is beginning to evaporate at a measurably elevated rate. The steam entering the atmosphere is beginning to contribute to the greenhouse effect. In the deepest ocean trenches and in the ocean at high latitudes, water temperatures are still near normal, having absorbed only a small fraction of the energy delivered to the surface. At 2 hours, surface temperatures globally are above 100 degrees Celsius in most regions. All surface and near-surface life is dead. The process is self-sustaining. The greenhouse feedback from water vapor is now operating, and the ocean will continue to evaporate over the following days and weeks as the surface temperature remains elevated. The deep subsurface is still at normal temperatures, insulated by kilometers of rock. The organisms in the deep biosphere are alive. The organisms in deep hydrothermal vent systems are alive. The total sterilization of the planet will require 1 million years or more as the heat slowly conducts into the deep rock, but the mechanism that will eventually achieve it has been irreversibly initiated. This 2-hour sequence, from the first moment of impact to the establishment of globally lethal surface conditions, is the physical basis for the 2-hour frame. It is not that everything is dead in 2 hours. It is that the conditions that will eventually kill everything have been established within 2 hours, and those conditions are now self-sustaining and irreversible. Vacuum decay. All of the extinction mechanisms discussed so far operate through physical processes that are in principle detectable, measurable, and theoretically survivable in some specific environment. The ocean vaporizing impact kills through heat, and heat takes time to propagate through rock. The gamma-ray burst kills through radiation, which is shielded by water and rock. Nuclear winter kills through cold and darkness, which can in principle be survived in underground bunkers or in the deep ocean. Even the most extreme naturally occurring astrophysical events leave physical environments where survival is theoretically possible. Vacuum decay is different in kind from all of these. It is not merely an event that would be difficult to survive. It is an event from which survival is physically impossible for anything anywhere. Understanding why requires understanding what the quantum vacuum is and why its current state might not be the most stable possible configuration. In quantum field theory, what we call empty space is not actually empty. It is filled with quantum fields that have a minimum energy state called the vacuum state. The energy of this vacuum state, the energy of nothing, is a physical quantity that contributes to the cosmological constant governing the expansion of the universe. The question that has occupied theoretical physicists since the discovery of the Higgs boson is whether the current vacuum state of these quantum fields is truly the lowest possible energy state, or whether it is merely a local minimum, a metastable state from which the fields could in principle transition to an even lower energy configuration if given sufficient perturbation. The analogy that is commonly used is a ball resting in a bowl partway up a hillside. The ball is in a stable position within the bowl. Small disturbances will not knock it out, but the bowl is not at the bottom of the hill. If the ball were given enough energy to escape the bowl, it would roll down to the bottom of the hill, which is at a lower energy level. The bowl represents the current vacuum state of the universe. The bottom of the hill represents a hypothetical lower energy vacuum state with fundamentally different physical properties. If the current vacuum of quantum fields is metastable rather than absolutely stable, then there exists in principle a lower energy vacuum state that could be nucleated somewhere in the universe through quantum tunneling. Quantum tunneling allows systems to pass through energy barriers that they could not cross classically, with a probability that depends on the height and width of the barrier. For vacuum decay, the relevant tunneling is the transition of a small region of space from the current vacuum to the lower energy vacuum. If such a transition were to occur, it would create a small bubble of the new vacuum surrounded by the current vacuum. The surface of this bubble, where the two vacuum states are in contact, would expand outward at the speed of light. Inside the bubble, the laws of physics would be different. The fundamental constants of nature, the mass of the electron, the strength of the electromagnetic force, the properties of the weak nuclear force, would all take different values determined by the lower energy vacuum state. The probability that any known chemistry would be possible in the new vacuum is negligible. The probability that atoms as we know them would be stable in the new vacuum is very small. Matter as we know it would cease to exist inside the expanding bubble. The expansion of the bubble cannot be stopped or slowed. It expands at exactly the speed of light, not because this is a coincidence, but because the speed of light is the maximum speed at which any influence can propagate through space. And the vacuum transition propagates as a phase front in the quantum field, rather than through any material medium. Nothing inside the bubble's expanding surface can affect anything outside it, because no signal from inside can outrun the bubble wall. The bubble would be completely undetectable until it arrived. Because it expands at the speed of light, there is no precursor radiation that can outrun it. The moment you could observe the bubble wall approaching would be the moment it arrived. More precisely, the moment the bubble wall reached your location would be the moment your atoms were converted from their current form to whatever form is possible in the new vacuum, which is likely nothing recognizable. This conversion would happen faster than any biological process. The neurons that carry sensory information fire at speeds of roughly 100 meters per second. The bubble wall moves at 3 times 10 to the 8 meters per second. By the time any signal could propagate through even a single neuron, the conversion would be complete across a region billions of times larger than a neuron. There would be no experience of vacuum decay, not even the experience of death, which requires biological processes to occur. There would simply be a state of the world in which certain atoms existed followed, at the boundary of the bubble, by a state in which they did not exist as those atoms. From the perspective of physics, the event is instantaneous at each location. From the perspective of anyone present, there is no event at all. One moment there is a biosphere, a civilization, a solar system. The next moment, from the reference frame of the universe outside the bubble, there is a sphere of new vacuum, expanding at the speed of light, containing whatever matter can be stable in the new physical regime. The question of whether the current quantum vacuum is stable or metastable is not resolved. The Higgs boson, discovered at CERN in 2012, has a mass of approximately 125.25 gigaelectron volts. Theoretical calculations of vacuum stability depend on the exact values of the Higgs boson mass and the top quark mass. With current measurements, the calculation suggests the vacuum sits in what is called a metastable region, not unambiguously stable, not unambiguously unstable. The uncertainty in the calculation comes primarily from higher-order quantum corrections that require the exact values of these masses at higher precision than currently available. If the vacuum is metastable, the rate of spontaneous vacuum decay anywhere in the observable universe is likely to be extraordinarily small, potentially negligibly small over the current age of the universe. The universe is approximately 13.8 billion years old and has persisted without apparent vacuum decay. This is itself evidence, though not proof, that spontaneous vacuum decay is rare. However, a process called seeded vacuum decay, in which an extremely high energy event creates the conditions for local vacuum transition, could in principle occur at much higher rates than spontaneous decay. Cosmic ray collisions with atmospheric nuclei occur continuously and at energies far exceeding anything achievable in particle accelerators. These collisions have been occurring for billions of years without apparent consequence, which is strong empirical evidence that vacuum decay cannot be triggered at those energies. The reason vacuum decay must be included in any complete inventory of total sterilization scenarios is not because it is likely. It is because it is physically possible under certain theoretical conditions, undetectable in advance, completely unsurvivable in any location, and total in a way that no other mechanism approaches. If a vacuum decay bubble is currently somewhere in the universe, expanding at the speed of light, and if it is aimed at the Milky Way, there is no observation that could detect it in advance and no action that could prevent its effects. This is the scenario that sits at the extreme of what physics permits: total, instantaneous, unavoidable, and in principle already in progress without any possibility of knowledge. The deep biosphere as the measure of extinction. The organisms that define the threshold between a mass extinction and a total sterilization are not the ones that populate common understanding of life. They are not mammals or birds or fish or insects or even plants. They are the extremophiles of the deep subsurface, organisms so unlike the familiar forms of life that their existence was not seriously contemplated by most biologists until the 1980s, and so hardy that the physical conditions required to kill them define the upper limit of what any extinction mechanism must achieve to be called truly total. Thermophiles and hyperthermophiles are organisms that grow optimally at temperatures far above what multicellular life can tolerate. The record-holding hyperthermophile, Methanopyrus candleri, was isolated from deep-sea hydrothermal vents and can reproduce at temperatures up to 122 degrees Celsius, higher than the boiling point of water at surface pressure. At the elevated pressures of deep-sea environments, water remains liquid above 100 degrees, allowing these organisms to function at temperatures that would destroy all surface biochemistry. The lower temperature limit for Methanopyrus growth is approximately 84 degrees Celsius. Below that temperature, the organism cannot reproduce, though it may be able to survive in a dormant state. Barophiles and piezophiles are organisms adapted to extreme pressure. In the deepest ocean trenches, such as the Mariana Trench at approximately 11 kilometers depth, the pressure is roughly 1,100 times the atmospheric pressure at sea level. Organisms adapted to these pressures have membrane compositions and protein structures that are stable only under high pressure and are actually disrupted at lower pressures. They are as specifically adapted to their high-pressure environment as surface organisms are to their low-pressure environment. Deinococcus radiodurans is often cited as the most radiation-resistant organism known. It can withstand gamma radiation doses of up to 1.5 million rads, approximately 3,000 times the dose that would kill a human, and resume normal reproduction after a brief period of DNA repair. Its resistance comes from an extraordinarily efficient DNA repair system that can reassemble a completely shattered genome from hundreds of fragments within a few hours. It is so radiation resistant that it was found growing in canned meat that had been irradiated as a sterilization procedure in the 1950s. Tardigrades, sometimes called water bears, are microscopic animals that are capable of surviving conditions lethal to virtually any other animal. In a dehydrated dormant state called a ton, tardigrades can survive temperatures from near absolute zero to 150 degrees Celsius, vacuum, intense radiation and desiccation for years to decades. They are not deep biosphere organisms, but surface and soil organisms. But their extraordinary resistance illustrates the range of physical conditions that the hardiest known organisms can survive. These organisms define the physical parameters that any total sterilization event must exceed. For deep rock organisms living at depths of 5 kilometers or more, the relevant parameters are temperature and pressure. To kill these organisms requires heating the rock they inhabit to above their thermal limit, approximately 130 degrees Celsius, for a sustained period. At depths of 5 kilometers, the current temperature is already elevated above surface conditions due to geothermal heat flow, typically between 100 and 150 degrees Celsius, depending on the geological setting. An extinction event that dramatically increases surface temperature would need to conduct that heat increase through 5 kilometers of rock to reach these organisms. Rock has a thermal conductivity of approximately 2 to 3 watts per meter per Kelvin and a heat capacity of approximately 800 to 1000 joules per kilogram per Kelvin. A rough calculation of how long it takes a temperature increase at the surface to propagate to a depth of 5 kilometers gives a result in the range of hundreds of thousands to millions of years. This is the physical basis for the claim that an ocean vaporizing impact initiates the process of total sterilization within 2 hours, but requires millions of years to complete it. The surface killing is rapid. The sterilization of the deep biosphere is geological. The implications for any proposed total sterilization mechanism are significant. To achieve total sterilization on a timescale of hours rather than millions of years requires a mechanism that delivers lethal conditions directly and simultaneously to all depths, not just to the surface. Vacuum decay achieves this because it alters the physical laws rather than delivering heat or radiation. The ocean vaporizing impact does not achieve it on a 2-hour timescale, but initiates an irreversible process that will eventually achieve it. No other naturally occurring mechanism is known to achieve total sterilization on any timescale shorter than geological. The sun's role in both life and death. The sun is not a static background in any assessment of Earth's biological future. It is a variable energy source that has been changing since its formation 4.6 billion years ago and will continue changing on timescales that span the entire remaining history of complex life on Earth. Understanding the sun's role in potential extinction scenarios requires understanding both the short-term variations that constitute space weather and the long-term evolution that will eventually render Earth's surface uninhabitable by any organism more complex than hyperthermophilic bacteria. The sun generates energy through nuclear fusion in its core, converting hydrogen to helium at a rate that gradually increases over the sun's lifespan as the helium ash accumulates and the core contracts and heats. This gradual brightening has been occurring throughout Earth's history. The sun today is approximately 30% more luminous than it was when Earth formed 4.6 billion years ago. This brightening is ongoing and will continue as the sun ages. Over the next billion years, the sun's luminosity will increase by approximately 10%, which is sufficient to drive Earth into a runaway moist greenhouse, a process that would eventually strip the planet of its oceans through photodissociation of water vapour in the stratosphere and loss of hydrogen to space. On shorter timescales, the Sun produces coronal mass ejections, bursts of magnetised plasma ejected from the solar corona that can strike Earth's magnetosphere and induce large electromagnetic disturbances in electrical infrastructure. The most powerful coronal mass ejection in recorded history is the Carrington event of 1859, which induced currents strong enough in telegraph lines to start fires and shock telegraph operators. A Carrington equivalent event in the modern world, with its global electrical infrastructure, would be devastating to technological civilization, but would not threaten the biosphere. Even the most extreme plausible solar storm could not kill deep ocean organisms or deep rock organisms. The catastrophic solar event that is sometimes discussed as a potential extinction threat is a solar superflare, an event orders of magnitude more energetic than any recorded solar flare. Solar superflares have been observed on other Sun-like stars, with flare energies exceeding typical solar flares by factors of 10 to 10,000. Whether the Sun itself is capable of producing such events is uncertain. The Sun's magnetic field is less complex than those of younger, more rapidly rotating stars that commonly produce superflares, and the observational record does not include any confirmed superflare from the Sun. But absence of confirmed events over a few centuries of observation does not constrain the rate of events on million-year timescales. A solar superflare 10,000 times more energetic than the largest recorded solar flare would produce a radiation pulse capable of severely damaging the ozone layer, comparable in some respects to the effects of a gamma-ray burst from greater distance. The biological effects on the surface would be significant: ozone depletion, elevated ultraviolet flux, disruption of phytoplankton, and surface food webs. But the shielding by the atmosphere and by the ocean's water column would protect deep biosphere organisms entirely. A solar superflare, even at the extreme end of what has been observed on other stars, would not achieve total sterilization. What the Sun will eventually do to Earth is a different story. In approximately 5 billion years, the Sun will exhaust its core hydrogen and expand through a red giant phase, growing to a radius potentially large enough to engulf Earth's orbit. Whether Earth is actually engulfed or merely scorched depends on the details of the Sun's mass loss during the red giant phase, which affects the gravitational relationship between the Sun and Earth's orbit. What is certain is that the luminosity of the Sun during the red giant phase will be thousands to tens of thousands of times its current value. The surface of Earth at that point will be fully sterilized by the radiant heat long before the Sun physically expands to Earth's orbital distance. This is the slow version of total sterilization, the one that will eventually occur with certainty on a timescale of billions of years. Supervolcanoes and their actual limits. Volcanic eruptions are the most commonly occurring large geological events with potential biological impact, and the most extreme volcanic events in Earth's history are responsible for 2 of the 5 major mass extinctions in the geological record. Understanding what supervolcanic eruptions can and cannot do, and where they fall in the spectrum between devastating mass extinction and total sterilization, requires looking at the actual numbers for the largest documented volcanic events and comparing them to the thresholds for complete biosphere erasure. The Siberian traps flood basalt province, associated with the Permian Triassic extinction approximately 252 million years ago, was the largest volcanic episode in the past 500 million years of Earth's history. Over a period of approximately 1 million years, volcanic eruptions in what is now Siberia produced an estimated 3 to 4 million cubic kilometers of lava, enough to cover the entire surface of the continental United States to a depth of roughly 400 meters. The eruptions released enormous quantities of sulfur dioxide and carbon dioxide, driving both short-term cooling from sulfate aerosols and long-term warming from carbon dioxide accumulation. The resulting ocean acidification, ocean anoxia, warming and disruption of the carbon cycle contributed to the extinction of approximately 96% of marine species and 70% of terrestrial vertebrate species. These numbers are staggering. The Permian Triassic extinction was the worst biological catastrophe in the history of complex animal life. And yet it did not end all life. It did not even come close to ending all life. Bacteria in the deep subsurface were entirely unaffected. Hydrothermal vent communities, shielded by kilometers of ocean, continued without interruption. Even many surface organisms survived, because the extinction, while catastrophic in its scale, occurred over a period of tens of thousands to hundreds of thousands of years, rather than hours or days. The very long timescale of the Siberian Traps eruptions, which produced their full effect over 1 million years, meant that even organisms in stressed surface environments had time to adapt, migrate, or find refugia. The Toba eruption of approximately 74,000 years ago is frequently cited as the most recent very large volcanic event with documented effects on human populations. Toba ejected approximately 2,800 cubic kilometers of material, making it roughly 100 times larger than the 1980 Mount St. Helens eruption and several times larger than any historical eruption. The volcanic winter that followed may have contributed to a significant population bottleneck in human populations, with some genetic evidence suggesting the total human population may have dropped to fewer than 10,000 individuals at some point during or after the event. A 500 cubic kilometer eruption, comparable to Toba, would kill millions of people in the immediate vicinity from pyroclastic flows, ashfall, and tsunamis, and could produce a volcanic winter lasting several years that would devastate agricultural systems globally. It would not threaten the biosphere. It would not threaten the continuation of life at any deep subsurface level. It would not even threaten the continuation of human civilization, though it would severely damage it. For a volcanic event to seriously threaten total sterilization, it would need to be orders of magnitude larger than the Siberian Traps. There is no known volcanic system on Earth capable of eruptions at that scale. The Yellowstone hotspot, frequently discussed in popular media as a supervolcano threat, has a caldera covering approximately 3,400 square kilometers and is capable of eruptions in the range of 1,000 to 2,000 cubic kilometers. Similar in scale to Toba. A full Yellowstone eruption would be a regional catastrophe and a global agricultural disruption. It would not be a biosphere-threatening event. The limiting factor for volcanic sterilization is the same as the limiting factor for any thermal extinction mechanism: the thermal conductivity of rock and the depth of the most resilient organisms. To kill organisms 5 kilometers underground requires heating the rock above them to lethal temperatures and maintaining that temperature long enough for the heat to conduct down. No volcanic eruption, however large, delivers energy in a form that can achieve this on any timescale relevant to biology. Volcanic eruptions heat the surface and atmosphere. They do not heat the deep crust. The separation between the surface and the deep biosphere is precisely the separation that protects against surface events, however extreme. The physics of rapid atmospheric loss. Life on Earth depends on the atmosphere for multiple reasons that go beyond simply providing breathable air. The atmosphere provides the pressure that keeps liquid water stable at surface temperatures. It provides the greenhouse warming that keeps the average surface temperature 33 degrees Celsius above what it would be on an airless planet. It provides the ozone layer that absorbs ultraviolet radiation. It provides the medium through which water cycles from ocean to land and back. Removing the atmosphere, or dramatically altering its composition on a short timescale, would produce effects on the biosphere that are in some respects more severe than direct thermal or radiation events. Because atmospheric effects interact with the entire surface simultaneously and remove the conditions on which surface life depends. The most dramatic example of rapid atmospheric change in Earth's history was the Great Oxygenation Event approximately 2.4 billion years ago, when cyanobacteria evolving oxygenic photosynthesis began producing molecular oxygen as a metabolic byproduct. The oxygen, which was toxic to most existing anaerobic organisms, accumulated in the atmosphere over millions of years and drove what may have been the largest extinction of life in Earth's history by percentage of affected lineages, though it is rarely classified alongside the Phanerozoic mass extinctions, because it occurred before the diversification of complex multicellular life. The Great Oxygenation Event was, however, a slow process, occurring over hundreds of millions of years. A rapid loss of the atmosphere is physically possible through several mechanisms. A sufficiently energetic impact can blow off portions of the atmosphere. During the late heavy bombardment, some of the largest impacts may have significantly depleted Earth's early atmosphere, which was then replenished by outgassing from the interior and delivery of volatiles by comets and asteroids. A nearby gamma-ray burst or supernova could, at sufficiently close range, strip away portions of the atmosphere through radiation pressure. A large magnetoflare from within a few hundred light-years could deliver enough energy to the upper atmosphere to cause significant mass loss. For organisms already in the deep subsurface, atmospheric loss is irrelevant. They do not breathe surface air. They do not depend on surface temperature. They do not need the protection of the ozone layer. For surface and ocean life, however, atmospheric loss or severe atmospheric disruption would be catastrophic. Without sufficient atmospheric pressure, liquid water is unstable at surface temperatures. Without the ozone layer, ultraviolet radiation sterilizes the surface. Without the greenhouse effect, the surface temperature drops to approximately -18 degrees Celsius. Any of these changes, if sustained, would eliminate surface and near-surface life. The rate at which these changes could occur depends on the triggering mechanism. A gamma-ray burst depletes the ozone layer within minutes of arrival, but does not remove the bulk atmosphere. Ozone is a minor constituent of the atmosphere, and its removal, while biologically catastrophic, does not affect atmospheric pressure or the basic greenhouse effect. Removing the bulk atmosphere requires much more energy and would take longer even in the most energetic scenarios. Mars lost its bulk atmosphere over hundreds of millions to billions of years as the solar wind eroded it in the absence of a protective magnetic field. Even the most energetic nearby astrophysical events would not achieve bulk atmospheric removal in hours. Nuclear winter and its true limits. Nuclear weapons represent humanity's closest approach to a self-generated extinction capability, and the nuclear winter scenario, in which the soot from burning cities and forests injected into the stratosphere by a large nuclear exchange blocks sunlight for years, is the most thoroughly analysed of the self-generated extinction threats. Understanding its true capabilities and its true limits is essential for an honest assessment of where it falls in the spectrum from civilization ending to biosphere ending. The global nuclear arsenal currently contains approximately 12,000 warheads, with approximately 2,000 on high alert, ready to be launched within minutes. A full exchange between the United States and Russia would involve the detonation of somewhere between 1,000 and 4,000 warheads over a period of hours. The explosions would ignite firestorms in targeted cities. Those firestorms would inject soot into the stratosphere, where it would remain for years because stratospheric soot cannot be washed out by precipitation. The reduction in sunlight from the stratospheric soot would cool the global surface temperature, shorten growing seasons, and devastate agricultural production across the Northern Hemisphere. Climate models developed to simulate nuclear winter scenarios have been refined substantially since the original analyses by Turco, Toon, Ackerman, Pollack, and Sagan in 1983. Current models, using more sophisticated climate simulations and more realistic estimates of soot injection, suggests that a full exchange between the United States and Russia could inject 50 to 150 million tons of soot into the stratosphere, producing global temperature drops of 5 to 15 degrees Celsius lasting for years. Agricultural failures would begin within the first summer after the exchange. The deaths from famine and disease following the initial blast casualties would be measured in billions over the first few years. The nuclear winter scenario is, by the standards discussed in earlier chapters, a civilization ending but not biosphere ending event. The temperature drops it produces, while severe for agriculture and for many surface ecosystems, are well within the range of temperature changes that life has survived in Earth's glacial periods. The ice ages of the Pleistocene, in which global temperatures were 4 to 6 degrees cooler than present, and glaciers covered much of the northern hemisphere, did not eliminate the biosphere. They eliminated many individual species and compressed ranges dramatically. But the diversity of life persisted. A nuclear winter, even a severe one, produces temperature changes in the same range as a major glaciation compressed into a shorter time frame. The organisms that would survive a nuclear winter include virtually all deep subsurface life, all deep sea life below the photic zone, most freshwater organisms in habitats not directly affected by the initial strikes, soil microbes across most of the world, seeds and spores capable of surviving years of dormancy, insects and other invertebrates in sheltered environments, and likely many vertebrate species in regions distant from the primary exchange areas. The biosphere would be profoundly damaged. Ecosystem recovery would take decades to centuries. The food webs that support current biodiversity would be severely disrupted. But life would continue, and over ecological and evolutionary timescales, diversity would recover. What nuclear weapons cannot do, even in the most extreme theoretical scenarios involving complete detonation of all warheads, is produce the thermal or radiation conditions required to kill organisms in the deep subsurface. The total energy in the global nuclear arsenal is approximately 5,000 megatons, or 5 gigatons of TNT equivalent. This is a large number by human standards, but a small number by geophysical standards. The energy released by a magnitude 9 earthquake, of which several have occurred in recorded history, is approximately 2 gigatons of TNT equivalent. The annual heat flow from Earth's interior, the geothermal heat generated by radioactive decay in the crust and mantle, is approximately 44 terawatts, equivalent to approximately 10 trillion times the energy of a large hydrogen bomb released continuously each year. The deep biosphere operates in this environment without difficulty. The addition of 5,000 megatons of nuclear energy at the surface would not be detectable in the geothermal signal at depths of 5 kilometers. The runaway greenhouse Venus is the most instructive example in the solar system of what happens to a habitable planet after it crosses the threshold into a runaway greenhouse state. At 465 degrees Celsius surface temperature, hot enough to melt lead, with an atmospheric pressure 92 times that of Earth's surface, a sky permanently obscured by clouds of sulfuric acid, and no liquid water anywhere on the surface, Venus presents the definitive portrait of what Earth would look like after total sterilization by thermal runaway. Understanding the mechanism by which Venus arrived at its current state, and the specific physical conditions required to initiate the same process on Earth, is essential for evaluating where the runaway greenhouse sits in the hierarchy of extinction mechanisms. Venus and Earth formed from similar material in similar regions of the early solar system. Their masses are nearly identical. Venus has 81.5% of Earth's mass, a difference smaller than the measurement uncertainty on many astrophysical quantities. Their densities are nearly identical. Their bulk compositions are nearly identical. The prevailing view among planetary scientists, supported by the high ratio of deuterium to hydrogen in Venus's current atmosphere, is that Venus once had liquid water, possibly for as long as 2 billion years. The deuterium to hydrogen ratio is approximately 150 times higher than Earth's current ratio. Since hydrogen escapes from the upper atmosphere more readily than the heavier deuterium, this enrichment indicates that Venus has lost an enormous quantity of water over its history. Water that was initially present and has since been lost to space through photodissociation and hydrogen escape. The mechanism by which Venus transitioned from a potentially habitable world to its current state is the moist greenhouse instability, which in sufficiently extreme form leads to a runaway greenhouse. The sequence begins when the stellar luminosity received by a planet exceeds a critical threshold. For Earth's current distance from the Sun, this threshold corresponds to a solar luminosity approximately 10% higher than current, which will not be reached for approximately 1 billion years. For Venus's orbital distance, which is approximately 0.72 times Earth's distance from the Sun, the received flux is approximately 1.9 times Earth's, and the threshold was likely crossed billions of years ago as the Sun gradually brightened during its main sequence evolution. Once the critical flux is exceeded, the sequence of events is as follows. Surface temperatures rise above the point where the ocean surface evaporation rate exceeds the condensation rate. Water vapor begins accumulating in the atmosphere. Water vapor is a potent greenhouse gas, substantially more so than carbon dioxide on a per-molecule basis for the relevant infrared wavelengths. The accumulation of water vapor increases the greenhouse effect, which raises surface temperatures further, which increases evaporation, which increases atmospheric water vapor, which increases the greenhouse effect. This is a positive feedback loop with no natural termination. The ocean does not simply reach a new equilibrium at a higher temperature. The feedback continues until all liquid water has evaporated and the ocean is gone. With the ocean gone, the water vapor in the atmosphere is exposed to ultraviolet radiation at high altitude, where it is dissociated into hydrogen and oxygen. The hydrogen, being very light, escapes Earth's gravity gradually over geological time. The oxygen either escapes as well, more slowly, or combines with surface minerals through oxidation reactions. Over millions to hundreds of millions of years, the water is entirely lost to space. Venus retains essentially no water today. The surface is desiccated. The rock is dry. The atmosphere is 96.5% carbon dioxide, with most of the remainder being nitrogen, traces of sulfur dioxide and other gases. Water is measured in parts per million. For Earth, the runaway greenhouse is not an immediate threat. The current solar luminosity is below the critical threshold for Earth's orbital distance. The amount of carbon dioxide that could be released by burning all accessible fossil fuel reserves, while significant for climate disruption, would not push Earth over the runaway threshold. The most sophisticated climate models suggest Earth would need to be warmed by approximately 60 degrees Celsius above its current global average temperature of 15 degrees Celsius to approach the runaway threshold. That magnitude of warming is far beyond what any realistic fossil fuel combustion scenario produces. However, a triggering event that delivered that much warming rapidly, either an ocean vaporizing impact initiating the thermal feedback, a nearby gamma ray burst destroying the ozone layer and initiating a different pathway to warming, or a dramatic increase in solar output, could in principle initiate the runaway process. Once initiated, the process is self-sustaining and cannot be reversed. Over a timescale of approximately 1 million years, Earth's surface would transition from its current state to a Venus-like state with surface temperatures in excess of 400 degrees Celsius. No known organism can survive at these temperatures. The deep biosphere, initially protected by kilometers of rock, would eventually be sterilized as the planetary surface equilibrates at its new temperature. The runaway greenhouse is therefore the slowest of the total sterilization mechanisms on this list, but the one that, once initiated, is most certain to achieve complete sterilization on timescales shorter than the replacement time for any biological community. It does not kill organisms in 2 hours. It creates the conditions that will eventually kill every organism within 1 million years. And it does so in response to a triggering event that might itself occur within hours. Magnetar flares and the radiation limit of life. In 2004, a magnetar designated SGR 1806-20, located approximately 50,000 light-years from Earth on the far side of the Milky Way galaxy, underwent a giant flare. In 0.2 seconds, it released more energy than the Sun emits in 250,000 years. The pulse of gamma radiation and X-rays from this flare was intense enough to ionize Earth's upper atmosphere from 50,000 light-years away, briefly and measurably disrupting the ionosphere in ways detectable by radio monitoring stations. The scientists who analysed the ionospheric disturbance noted that had the magnetar been located at 10 light-years rather than 50,000, the flare would have been catastrophic for Earth's atmosphere and surface life. A magnetar is a neutron star with an extraordinarily intense magnetic field, typically around 10 to the 15 Gauss, compared to Earth's field of approximately 0.5 Gauss and the Sun's global field of approximately 1 to 5 Gauss. A neutron star itself is already an extreme object, the collapsed core of a massive star after a supernova, with a mass between 1.4 and 2.2 times the Sun's mass, compressed into a sphere approximately 12 kilometers in diameter. A teaspoon of neutron star material weighs approximately 10 million tons at the densities found in a neutron star's crust and interior. The magnetic field of a magnetar is so intense that it significantly affects the quantum mechanical structure of atoms, stretching electron orbitals in the field direction and affecting the chemical and physical properties of matter in the vicinity. Magnetar flares originate from sudden rearrangements of the neutron star's crust, called starquakes. The crust of a neutron star, though only about 1 kilometer thick, is under enormous stress from the intense magnetic field. When the stress exceeds the crust's yield strength, it fractures and reorganizes, releasing magnetic energy in a burst of gamma rays and X-rays. The 2004 SGR 1806-20 flare was the largest such event ever recorded. Its energy release in 0.2 seconds was approximately 2 times 10 to the 46 joules, a number so large that meaningful comparison requires context. The Sun's total luminosity over its entire 10 billion year lifespan is approximately 1.2 times 10 to the 44 joules. The magnetar flare outpaced the Sun's entire lifetime output by a factor of about 17 in a fifth of a second. At 50,000 light-years, this event ionized Earth's upper atmosphere, scaling the effect to shorter distances. At 10 light-years, the flux would be 25 million times greater, which would deliver a dose to Earth's atmosphere sufficient to completely destroy the ozone layer globally within minutes, and likely to initiate significant atmospheric mass loss. At distances of 1 to 2 light-years, a flare of comparable energy would deliver doses sufficient to sterilize the surface to considerable depth and to produce severe damage to the atmosphere on timescales of minutes. The critical shielding provided by Earth's atmosphere for surface life is real but finite. Gamma radiation with energies above approximately 1 eeMeV, mega-electron volt, is absorbed primarily in the upper atmosphere, depositing its energy in the stratosphere and mesosphere rather than reaching the surface. This atmospheric shielding is what protects surface life from cosmic gamma-ray events at distances of thousands of light-years. But there is a threshold beyond which the atmosphere is no longer sufficient. When the flux of high-energy photons becomes large enough that the atmosphere's absorbing capacity is overwhelmed, and some fraction penetrates to the surface. For magnetar flares at very short distances, this threshold could be exceeded. At distances of a few hundred light-years, a giant flare could deliver doses to the surface that exceed the survival threshold for most surface organisms. At distances of tens of light-years, the surface dose would likely be lethal to all surface organisms. At distances of less than 1 light-year, The radiation would be intense enough to penetrate significant depths of rock and water, beginning to threaten organisms in shallow subsurface environments. Whether a magnetar at any currently known distance could threaten the deep biosphere through radiation alone is doubtful. The attenuation of gamma radiation through rock is substantial. For rock of typical density, the half-value layer for high-energy gamma radiation is approximately 10 to 20 centimetres. To attenuate a surface dose by a factor sufficient to protect organisms 5 kilometres deep would require roughly 10,000 half-value layers, corresponding to a reduction of 10 to the 3,000, an attenuation factor that effectively eliminates the surface dose, regardless of its initial intensity. Even an extraordinarily intense flare at close range would not deliver a lethal dose to organisms at 5 kilometre depth through the mechanism of direct radiation penetration alone. However, radiation is not the only mechanism by which an extreme magnetar flare could threaten the deep biosphere. Atmospheric loss is the more relevant concern at very close distances. If the flare were close enough and energetic enough to drive off a substantial fraction of the atmosphere, the subsequent exposure of the surface to solar ultraviolet radiation without atmospheric protection would initiate the sequence of surface sterilization. More critically, if the energy delivered by the flare was sufficient to heat the surface significantly, the thermal coupling between the surface and the deep subsurface would eventually reach the deep biosphere on geological timescales. The current risk assessment for magnetar flares is low. No known magnetar is within the dangerous range. The nearest known neutron stars are at distances of several hundred light-years, and magnetars are rarer than ordinary neutron stars. The probability of a lethal magnetar flare directed at Earth within any human timescale is negligibly small. But the mechanism is real, the physics is clear, and the event that occurred 50,000 light-years away in 2004 demonstrated that the universe does produce events of this character, the engineered pathogen ceiling. Any complete inventory of extinction threats must include self-generated biological threats and specifically the question of whether an engineered pathogen could serve as a total sterilization mechanism. The reference transcript discusses this in terms of what an engineered pathogen could and could not accomplish, and the physical analysis supports a clear conclusion. No conceivable pathogen, natural or engineered, could achieve total sterilization of life on Earth. Understanding why requires understanding both the limits of pathogen biology and the nature of the most resistant life on Earth. Pathogens are biological entities, parasites or predators at the molecular level that exploit the specific biochemistry of their hosts to replicate themselves. Every pathogen has a host range, a set of organisms whose cellular machinery is compatible with the pathogen's replication mechanism. The more specific the molecular match required between pathogen and host, the narrower the host range. Most human pathogens cannot infect bacteria. Most bacterial pathogens cannot infect plants. The mechanisms of infection and replication are sufficiently distinct across the major domains of life that no single pathogen infects organisms from all domains. To achieve total sterilization through a biological agent, a pathogen would need to infect and kill organisms across bacteria, archaea, and eukaryotes, spanning the full range of environments from the deep subsurface to hydrothermal vents to soil to ocean to atmosphere. The cellular machinery of a deep subsurface hyperthermophilic archaeon operating at 120 degrees Celsius and 500 atmospheres of pressure is so different from the cellular machinery of a surface eukaryote that no single replication mechanism could exploit both. The molecular structures used by a surface pathogen as attachment receptors and replication substrates do not exist in the same form in deep subsurface organisms. Beyond the host range limitation, pathogens require specific environmental conditions to remain viable and infectious between host contacts. Temperature, humidity, UV exposure, and chemical environment all affect pathogen survival outside the host. An engineered pathogen designed to spread globally among surface organisms would have no mechanism for reaching organisms kilometres underground in rock fractures. The pathogen could not survive transport through that geological environment, even if it was somehow delivered to the surface above those organisms. The most dangerous category of engineered pathogen for human civilization is one optimized for human transmission and lethality. A virus combining the aerosol transmissibility of influenza or measles with the lethality of Ebola or smallpox, potentially with modifications to evade immune recognition. Such a pathogen could, in a worst-case scenario, spread to most of the human population within months of release and kill a large fraction of those infected. The consequences for human civilization would be catastrophic. The consequences for the biosphere would be comparatively modest. The loss of most humans, with secondary effects on the ecosystems humans currently manage or disturb. But no direct effect on most species, and no effect at all on the deep biosphere or the microbial foundation of the planet. Even a hypothetical pathogen engineered to infect all mammals would not achieve total sterilization. The insects, which represent the dominant animal biomass and the ecological foundation of most terrestrial ecosystems, use fundamentally different cellular machinery than mammals. The plants, which produce most of the organic carbon entering terrestrial food webs, have no susceptibility to animal pathogens. The bacteria and archaea in the deep subsurface and hydrothermal vents would be entirely unaffected. The ocean ecosystem, which depends primarily on phytoplankton and zooplankton, rather than on any organism susceptible to mammalian pathogens, would continue functioning. Biological weapons, even at the extreme end of what might be engineered, fall firmly in the category of civilization-ending threats rather than biosphere-ending threats. They represent perhaps the most acute near-term risk to human civilization from the category of self-generated threats, but they do not threaten the continuation of life itself. The biosphere has survived the Permian extinction. It has survived the Chicxulub impact. It would survive even the worst conceivable bioweapon attack, though the recovery of complexity after a severe pandemic that eliminated most large animals might take tens of millions of years. The compounding of simultaneous threats. Most analyses of extinction risks treat individual threats in isolation. An asteroid impact is analysed for its specific physical effects. A gamma-ray burst is analysed for its ozone depletion consequences. A supervolcanic eruption is analysed for its atmospheric injection. But the history of Earth's actual extinction events reveals that the worst of them were driven not by single causes, but by the compounding of multiple simultaneous stresses, each one reducing the biosphere's resilience and making subsequent stresses more lethal than they would have been in isolation. The Permian Triassic extinction, which remains the most severe mass extinction in the history of complex animal life, illustrates this compounding in detail. The Siberian Trap's volcanism was the primary trigger, but its effects operated through multiple distinct pathways simultaneously. Direct volcanic emissions of sulfur dioxide produce brief but intense cooling from sulfate aerosols. The longer-term release of carbon dioxide from the eruptions drove warming that persisted after the sulfate aerosols settled. The warming drove ocean stratification, which reduced the mixing of cold, oxygenated deep water with the warmer surface. Reduced mixing led to ocean anoxia, as oxygen in the deep water was consumed by decomposition without replenishment. The anoxic water produced by bacterial decomposition of organic matter in the absence of oxygen became enriched in hydrogen sulfide, which is directly toxic to most aerobic organisms. Hydrogen sulfide that escaped to the atmosphere was toxic to terrestrial life and also photochemically active in ways that damaged the ozone layer. Simultaneously, the warming caused by CO2 acidified the ocean as CO2 dissolved in seawater, forming carbonic acid, impairing the ability of calcifying organisms to build shells and skeletons. Each of these processes reinforced the others, and the combination was more lethal than any single process would have been in isolation. The concept of simultaneous compounding threats is directly relevant to the question of what could end all life within 2 hours, rather than over millions of years. In isolation, no individual mechanism currently available in Earth's cosmic neighbourhood can achieve total sterilization on a 2-hour timescale. The ocean vaporizing impact initiates it, but requires millions of years to complete. The gamma-ray burst depletes the ozone layer, but leaves the deep biosphere intact. The magnetar flare is catastrophic at close range, but attenuated to non-lethal levels in the deep rock. But consider a scenario in which a large gamma-ray burst, large enough to severely deplete the ozone layer globally, is followed within months by a major impact. The gamma-ray burst has left the surface life devastated. Food webs are collapsing. The ozone layer is compromised. The biosphere is at its most vulnerable. Into this already severely stressed biosphere, a moderate impact, one not large enough by itself to initiate the runaway greenhouse, adds atmospheric soot, acid rain, seismic disruption and regional thermal pulses. The combined effect could push the system across thresholds that neither event alone would cross. This compounding scenario is speculative in the specific combination described, but the general principle is well supported by the geological record. The Cretaceous-Paleogene extinction shows evidence not only of the Chicxulub impact, but also of contemporaneous large-scale volcanism from the Deccan Traps in what is now India. Whether the Deccan volcanism was caused by the impact, as some researchers have proposed through seismic triggering, or was coincidental, its coincidence with the impact created a more severe and prolonged extinction event than the impact alone would have produced. The practical implication is that the 2-hour threshold for initiating the sequence of total sterilization is easier to reach through compounding than through any single mechanism. A series of large impacts occurring over a short geological period could push Earth from mass extinction to total sterilization by preventing any recovery between events, similar to what may have occurred during the most intense phases of the late heavy bombardment. Individual events that would each be survivable in isolation become collectively unsurvivable when their effects overlap. The reason compounding matters so much is that biological systems possess resilience rather than invulnerability. Ecosystems can absorb extraordinary shocks provided enough of their underlying structure remains intact. Species can survive climatic disruption if suitable refuges persist. Ocean life can survive surface catastrophes if deep water environments remain habitable. Microbial communities can survive planetary-scale disasters if energy sources remain available underground. The history of life on Earth is, in large part, a history of resilience operating through these refuges. What multiple simultaneous catastrophes threaten is not life directly, but the existence of refuges. Each additional stress removes another category of survival strategy. A severe impact may devastate the surface while leaving deep oceans and subterranean ecosystems intact. A gamma-ray burst may damage the atmosphere while leaving underground microbial communities largely unaffected. A supervolcanic eruption may disrupt climate without significantly affecting deep crustal habitats. When these events occur together or in rapid succession, the number of remaining refugees decreases rapidly. This principle appears repeatedly in ecological collapses at smaller scales. Modern ecosystems rarely fail because of a single pressure. Coral reefs are stressed simultaneously by warming, acidification, pollution, overfishing, and disease. Forests face drought, invasive species, fire, and habitat fragmentation. The collapse occurs when multiple pressures interact, reducing the system's ability to compensate for any one of them. The same logic applies at planetary scales. A useful way to think about extinction risk is not as a question of how powerful a catastrophe is, but of how many independent survival pathways remain after it occurs. Following the Chicxulub impact, many ecological pathways were destroyed, but enough remained for life to recover. Deep-sea ecosystems survived. freshwater habitats persisted. Microbial communities remained widespread. The biosphere contracted dramatically, but it retained enough diversity and enough habitable environments to rebuild. Total sterilization requires something more extreme. It requires eliminating not only dominant organisms, but also the environments that allow recovery. A catastrophe capable of heating the oceans, poisoning the atmosphere, sterilizing the upper crust, and disrupting deep subsurface habitats simultaneously would attack multiple layers of biological resilience at once. The probability of any single event accomplishing this is extraordinarily low. The probability increases when multiple events contribute different destructive mechanisms. This is one reason the geological record contains numerous mass extinctions, but no confirmed example of complete planetary sterilization after life first became established. Catastrophes capable of destroying ecosystems are relatively common on geological timescales. Catastrophes capable of removing every refuge are vastly rarer. Earth's biosphere has repeatedly demonstrated that surviving a disaster and thriving after a disaster are very different things. Recovery can take millions of years, but survival requires only a tiny remnant population occupying a suitable environment. The distinction becomes crucial when discussing the destruction of all life. Extinction is often imagined as a single moment, a final event after which nothing remains. In reality, the final survivors are likely to exist in places far removed from the environments that dominate the surface. The last organisms would not be large animals or complex plants. They would be microbes living deep underground, sustained by chemical energy sources independent of sunlight and protected from conditions that would be lethal elsewhere. Any scenario claiming to destroy all life must account for those refuges as well. The challenge is therefore not merely creating a catastrophe, it is creating a chain of catastrophes capable of systematically eliminating every remaining place where biology can retreat. That requirement raises the threshold for total sterilization far beyond the threshold for even the most severe mass extinction events in Earth's history. What happens inside the 2-hour window? The 2-hour window that defines the initial killing phase of the most rapid total extinction mechanism deserves detailed examination. The ocean vaporizing impact scenario, which represents the most physically documented pathway to initiation of total sterilization, produces a specific sequence of events during those 2 hours that can be traced with reasonable confidence from the known physics of large impacts, atmospheric re-entry heating, and thermal radiation transport. Walking through this sequence in detail makes concrete what the phrase "end of all life in 2 hours" actually means physically. Time zero, the moment of impact. The impactor, 500 kilometers in diameter, traveling at 20 kilometers per second, reaches Earth's surface. At 20 kilometers per second, it covers the distance from Earth's atmosphere to the surface in approximately 3 seconds. The atmosphere offers essentially no resistance to an object of this size at this velocity. The compression of air beneath the impactor heats it to plasma temperatures of 50,000 Kelvin or more. The impactor and the surface rock at the impact site vaporize simultaneously. The energy of the impact, approximately 3 times 10 to the 30 joules, is released in a time comparable to the duration of a large nuclear weapon detonation, but with 60 billion times the energy. First minute, the crater forms. For an impactor 500 kilometers in diameter, the resulting crater would have an initial diameter of several thousand kilometers. The crust at the impact site is not merely excavated, but vaporized and blown outward in a fireball that engulfs the surrounding continent. The ejector column, the material blasted upward by the explosion, reaches the upper atmosphere within seconds of the impact and begins escaping into space within the first minute. The seismic energy propagating outward through the crust at 8 to 13 kilometers per second has traveled 480 to 780 kilometers from the impact site within the first minute. Earthquakes of unprecedented magnitude have begun registering at recording stations worldwide, minutes 2 through 5. The ejector column continues to expand upward and outward. The material blasted into space fans out on ballistic trajectories that will return it to the atmosphere globally over the following tens of minutes. The seismic wave reaches a radius of approximately 3,000 kilometers from the impact site within 5 minutes, producing catastrophic ground motion across a continent-scale region. All structures within this radius have collapsed. The fires ignited by the thermal radiation of the initial fireball are spreading outward from the impact site. Minutes 5 through 20. The first ejector returning from space begins entering the atmosphere globally. These are the fast-moving fragments that were blasted upward at the highest velocities and followed the most direct ballistic trajectories back to Earth. Each fragment heats as it decelerates in the upper atmosphere, producing a brief trail of heated air. With an enormous quantity of fragments returning simultaneously, the upper atmosphere over the entire sunlit hemisphere begins glowing. The infrared radiation from this glowing upper atmosphere begins reaching the surface. An observer anywhere in the world not sheltered below ground would notice the sky beginning to brighten from above rather than just from the sun. Minutes 20 through 40. The seismic wave from the impact has now crossed most of the planet. The antipodal point, the location on the exact opposite side of Earth from the impact, experiences converging seismic waves that produce amplified shaking. Large-scale geological disruption is occurring globally. Landslides, volcanic triggering, submarine slides generating additional tsunamis. The global sky is now luminous from ejector re-entry. The surface temperature in exposed locations is beginning to rise measurably. The rate of ejector re-entry is reaching its peak, producing the maximum rate of atmospheric heating, minutes 40 through 60. Surface temperatures in exposed locations have risen from ambient to 40 to 50 degrees Celsius. This rate of temperature increase would be perceived as rapid and alarming, but would not yet be immediately lethal to most organisms. Exposed animals are experiencing heat stress. Birds in flight are affected by the heated air. Insects in exposed locations are dying. Ocean surface temperatures are beginning to rise, initially at the surface and most rapidly in regions where the sun is directly overhead. The sky is extremely bright from the combined effect of ejector re-entry heating and the smoke beginning to rise from fires that have ignited in the driest regions. Hours 1 through 2. Surface temperatures in exposed locations continue rising. By 90 minutes, temperatures in most surface locations have exceeded 60 degrees Celsius, the threshold for rapid death in most vertebrates. By 2 hours, surface temperatures in most regions have exceeded 80 to 100 degrees Celsius. The ocean surface is beginning to generate more steam than usual, and the steam is accumulating in the atmosphere. All surface organisms that have not burrowed into soil or entered water are dead or dying. Aquatic organisms in shallow water are experiencing lethal temperatures. The ocean below the surface mixed layer, roughly the top 100 meters, is still at near normal temperatures, and organisms at these depths are still alive. Organisms in the deep ocean and in the deep subsurface are entirely unaffected. At the 2-hour mark, all surface life is dead. Shallow freshwater life is dead. Shallow marine life is dying rapidly. The deep ocean remains habitable for now. The deep subsurface remains habitable for now. The global surface temperature is above 100 degrees Celsius and rising. The positive feedback from water vapor accumulation has been initiated. The atmosphere is not going to cool back to normal. The process is self-sustaining. What took 2 hours to begin will take 1 million years to complete. This 2-hour sequence is the physical basis for the claim that total sterilization can be initiated within 2 hours. The initiation is not the same as the completion. The deep biosphere will still be alive for hundreds of thousands of years after the impact. But the process that will eventually reach and kill those organisms has been irreversibly initiated within the first 2 hours, and no physical process can interrupt or reverse it. The biological meaning of the deepest survivors. The organisms that are the last to die in any total sterilization scenario are not the largest or most complex. They are not the organisms most people think of as representing life. They are bacteria and archaea living in conditions that would be instantly lethal to any surface organism, sustained by chemical reactions in hot, dark rock kilometers underground. Understanding what these organisms actually are and how they sustain themselves illuminates not only the resilience of life, but also the physical conditions required to end it. The deep subsurface biosphere was not seriously investigated until the 1980s, when oil drilling and geomicrobiology began providing access to rock samples from depths beyond the reach of contamination by surface organisms. The first unambiguous identification of living bacteria from depths exceeding 1 kilometre was published in 1987 by Todd Stevens and James McKinley at Pacific Northwest National Laboratory, working with samples from basalt aquifers approximately 1.5 kilometres below the Columbia River Plateau in Washington state. The organisms they found were living on hydrogen produced by the reaction of water with basalt rock, a chemical reaction that requires no sunlight and no organic carbon from the surface. This discovery opened the field of deep biosphere research, and subsequent decades of investigation have pushed the depth record for living organisms to more than 5 kilometres in continental crust and more than 3 kilometres below the seafloor in oceanic crust. The organisms found at these depths are metabolically diverse. Some use hydrogen as their energy source, some use methane, some use iron, some use sulfur compounds. The energy available from these chemical sources is orders of magnitude less per unit volume than the energy available in a sunlit surface environment. The organisms have adapted to this extreme energy poverty by slowing essentially every aspect of their biology. A bacterium in a fertile soil environment might divide every 20 minutes. A bacterium in a laboratory culture with ample nutrients might divide every hour. A bacterium in the deep subsurface might divide once every 10,000 years. The calculation is not metaphorical. Based on measurements of chemical fluxes through deep rock environments and the energy requirements of cellular maintenance, some researchers have estimated that individual cells in the deepest subsurface environments spend the vast majority of their time in a state of minimal activity, doing essentially nothing detectable, consuming just enough energy from ambient chemical gradients to maintain their molecular integrity against the degradation that would otherwise occur over geological time. These organisms are not sleeping in any biological sense. Sleep involves active neurological processes. These organisms are simply proceeding at a pace of metabolic activity so slow that it is measurable only by the most sensitive chemical techniques averaged over years to decades of observation. A single cell might not produce a measurable quantity of metabolic byproduct in the course of an experiment lasting months. The only evidence that it is alive rather than dead is its continued cellular integrity, its intact membranes and functional molecular machinery, and the fact that it eventually produces a daughter cell. The thermal tolerance of these deep organisms is the property most relevant to their role as the ultimate survivors. The hyperthermophiles at the extremes of the temperature range for life grow optimally at temperatures between 80 and 120 degrees Celsius and have been found to survive brief exposure to even higher temperatures. The high temperature limit for any known organism is approximately 122 degrees Celsius, the growth maximum for Methanopyrus candleri at high pressure. This temperature limit is set by the thermodynamics of protein folding and DNA stability. Above approximately 130 degrees Celsius, the thermal energy becomes sufficient to denature proteins and melt the double-stranded DNA even in organisms with the most heat-stable molecular structures known. The significance of this temperature limit for the total sterilization question is that 122 to 130 degrees Celsius represents the finish line that any extinction mechanism must cross in every location where organisms could be present to achieve complete sterilization. Currently, in many parts of Earth's deep subsurface, temperatures are already in the range of 50 to 120 degrees Celsius at depths of 2 to 5 kilometers due to the geothermal gradient. Organisms living at temperatures of 90 to 110 degrees Celsius underground are already near their thermal limit. An extinction event that increased the geothermal heat flow substantially, either by depositing enormous amounts of energy at the surface that eventually conducted downward, or by dramatically increasing volcanism through impact-triggered mantle disruption, could push these already thermally stressed organisms past their limits more quickly than the simple surface-to-depth thermal conduction calculation suggests. What makes these organisms such formidable survivors is that temperature is only one of the variables they have adapted to. The deep biosphere is also characterized by extreme pressure, limited nutrient availability, high salinity in some environments, and complete isolation from the surface for timescales that can extend into the millions of years. Genetic studies of subsurface microbial communities have identified populations that appear to have been separated from the surface biosphere for geological periods longer than the existence of many modern species. These organisms are not simply hiding underground. They are inhabitants of a distinct planetary environment that happens to exist beneath the one visible at the surface. This distinction matters because most extinction scenarios are surface phenomena. Asteroid impacts devastate continents and oceans. Gamma-ray bursts alter atmospheric chemistry. Supernova radiation affects the upper atmosphere. Even the most severe climate disruptions operate primarily through changes in temperature, precipitation, ocean circulation, and ecosystem structure near the surface. The deep biosphere experiences these events only indirectly. A catastrophe capable of exterminating every plant and animal on Earth may leave deep microbial ecosystems largely unaffected for thousands or even millions of years. The persistence of these environments is partly a consequence of the physical properties of rock itself. Rock is an excellent shield against many forms of radiation. A few meters of rock can reduce radiation exposure dramatically. A few kilometers can render even extreme cosmic radiation events largely irrelevant to the organisms below. The same insulation slows temperature changes. While the atmosphere can heat or cool over years or decades, heat moves through solid rock much more slowly. Conditions several kilometers underground are therefore buffered against rapid environmental fluctuations occurring at the surface. This creates a profound asymmetry in extinction risk. It is comparatively easy on geological timescales to destroy complex ecosystems. It is extraordinarily difficult to sterilize a planet. The requirements for complete sterilization are not defined by the vulnerabilities of forests, coral reefs, or large animals. They are defined by the resilience of the most durable microorganisms occupying the most protected habitats. Any proposed mechanism for ending all life must ultimately overcome those organisms and those environments. The deep biosphere therefore serves as a kind of biological benchmark for planetary survival. As long as chemically active liquid water exists within the crust and temperatures remain below the stability limits of proteins and DNA, some form of microbial life is likely to persist. The final extinction of life on Earth would not occur when the last forest burns, the last ocean ecosystem collapses, or the last animal dies. It would occur when conditions become hostile even to these organisms, the slowest living, deepest buried, and most resilient inhabitants of the planet. Only then would Earth become truly sterile. The rarity of total sterilization events in Earth's history. Earth is approximately 4.6 billion years old. Life has been present for at least 3.8 billion of those years, and quite possibly longer. During those 3.8 billion years, Earth has experienced 5 major mass extinctions, hundreds of minor mass extinctions, multiple large impact events, multiple episodes of intense volcanism, multiple glaciations severe enough to potentially have covered the entire ocean in ice, and the gradual brightening of the sun by approximately 30%. Through all of this, the continuity of life has never been broken. The deep biosphere has never been fully sterilized. This empirical fact is itself a statement about the frequency and severity of total sterilization events in Earth's history. If total sterilization events were common, life would not have a continuous 3.8 billion year history. The geological and biological record of Earth is a record of survival through catastrophes that were severe enough to reset the surface biosphere repeatedly, but never severe enough to reach the deep organisms who constituted the ultimate refuge from which recovery always occurred. The late heavy bombardment, approximately 3.9 to 3.8 billion years ago, is the period in Earth's history most likely to have produced impacts approaching the ocean vaporization threshold. The flux of large impactors on the inner solar system during this period was dramatically higher than the current rate. Some analyses of the lunar crater recorded suggest that during the most intense phase of the bombardment, an impactor of Chicxulub size or larger was striking the Moon every few million years. For Earth, which has a larger cross-section and stronger gravitational focusing, the rate would have been substantially higher. Whether any impacts during the late heavy bombardment crossed the ocean vaporization threshold on Earth is unknown. The geological record from this period is almost entirely destroyed by subsequent plate tectonic recycling of the crust. The oldest rocks preserved on Earth's surface are approximately 4.0 billion years old, and the geological continuity of the record does not extend to the most intense period of the bombardment. What is known is that life existed on Earth within the bombardment period itself, as evidenced by carbon isotope ratios in ancient sediments suggesting biological fractionation of carbon at approximately 3.8 billion years ago. This evidence does not prove that life survived the bombardment continuously from an earlier origin. It is consistent with life having been driven to near extinction by impact events and recovering from survivors in the deep subsurface, with the post-bombardment period representing one of potentially multiple recovery events. The most important implication of Earth's 3.8 billion year biological history is that the mechanisms capable of total sterilization are rare on the timescale of a planetary lifetime. The odds of total sterilization occurring in any given year, or even any given million years, are very small. The planet has been protected by the low current rate of large impactors, by the absence of nearby gamma-ray burst progenitors in the dangerous distance range, by the sun's current relatively quiet behavior, and by the fundamental robustness of the deep biosphere which has survived everything the universe has thrown at it so far. But rare is not impossible. Rare on the timescale of human civilization is not the same as rare on the timescale of planetary systems. An event that occurs once in a billion years will occur approximately 4 times in Earth's remaining billion or so years of habitability, before the brightening sun drives the runaway greenhouse without any triggering event. The question of how to think about rare catastrophic risks requires placing them in the appropriate temporal context, which in this case is the remaining lifespan of Earth as a habitable planet. The philosophical dimension, the discussion of mechanisms that could end all life on Earth, necessarily raises a question that is simultaneously the simplest and the hardest in biology. What is life? The question matters for the practical analysis of extinction scenarios, because the answer determines what must be killed to achieve total sterilization. If life is only the organisms we can observe, many mechanisms suffice. If life is the entire distributed biosphere extending to 5 kilometers depth across the entire planetary crust, only the most extreme mechanisms qualify. The operational definition used by astrobiologists and astrobiology-adjacent researchers is the set of systems capable of Darwinian evolution. Systems that can self-replicate with heritable variation, that compete for limited resources, and that thereby undergo natural selection leading to adaptation. Under this definition, a single bacterium is alive. A prion, which is a misfolded protein capable of converting correctly folded versions of the same protein to the misfolded form, might or might not be alive, depending on whether one considers the conversion a form of replication with heritable variation. A virus is alive under some definitions and not others. For the purposes of the extinction question, the most useful definition is ecological. Life is the sum total of all self-replicating systems that participate in energy and material cycling on Earth, from the surface to the greatest accessible depth. This includes not only the organisms visible to the eye, but the entire deep biosphere, the viruses that infect those organisms, the prions and mobile genetic elements that parasitize them, and potentially even some self-catalyzing chemical systems at the margins of what most biologists would call life. Under this ecological definition, ending all life requires not just killing surface organisms, but eliminating every system capable of self-replication in every environment accessible to biology on Earth. This is a much higher bar than most extinction discussions acknowledge. It requires conditions lethal to hyperthermophiles at 5 kilometers depth. It requires conditions lethal to piezophiles in the deepest ocean trenches. It requires conditions lethal to the radiation-resistant Deinococcus and its relatives. It requires conditions lethal to spore-forming organisms that can persist in dormancy for millions of years. The resistance of life at its extremes has been repeatedly demonstrated. Life in deep-sea hydrothermal vents was not suspected to exist until its discovery in 1977 by the Alvin submersible near the Galapagos Rift. The discovery fundamentally changed understanding of the range of conditions compatible with life. Life in the deep subsurface was not suspected by most scientists until the 1980s, when direct evidence began accumulating from drill core studies. Each time researchers have investigated an environment considered too extreme for life, they have found organisms capable of living there. This pattern of discovery suggests that the actual distribution of life on Earth is probably still incompletely mapped, and that the most extreme environments currently thought to be lifeless may contain organisms not yet identified. The implications for the total sterilization question are sobering. If life occupies every environment on Earth where the basic physical and chemical requirements are marginally met, the task of ending all life requires eliminating all such environments simultaneously, rather than just eliminating the obvious surface environments where most of Earth's visible biodiversity resides. The philosophical dimension of this analysis is the recognition that life is not fragile. It is not something that exists at the pleasure of favorable surface conditions. It is a property of planetary systems that penetrates their accessible volumes comprehensively and adapts to exploit any available energy gradient. The image of life as a thin, vulnerable film on the surface of a planet, easily destroyed by cosmic events, is inaccurate. Life is more accurately a planetary phenomenon, distributed throughout a significant fraction of the planet's accessible volume, chemically diverse, thermally and mechanically tolerant at its extremes, and remarkably persistent across geological time. This does not mean life is indestructible. The mechanisms discussed in this script are capable of ending it, but they are capable of ending it only by fundamentally restructuring the physical conditions of the planet in ways that take geological time to propagate through the full volume of inhabited rock. The total sterilization of Earth is a geological event, not a biological one. There is an irony in this conclusion. Human beings tend to evaluate the health of the biosphere through the organisms most visible to us. Forests, coral reefs, birds, mammals, and flowering plants dominate our perception of life, because they dominate our everyday experience. Yet from a biological perspective, these organisms represent only a thin and highly specialized layer of a much larger system. Most of Earth's biomass is microbial. Most of Earth's evolutionary history was microbial. For roughly 3 billion years after life first appeared, the planet contained no animals, no plants, and no complex ecosystems of the kind that now seem inseparable from the concept of a living world. Life existed entirely in forms that many people would not recognize as life if they encountered them in isolation. That perspective changes how extinction itself must be understood. The disappearance of humanity would not be the end of life. The extinction of all mammals would not be the end of life. Even the loss of every visible multicellular organism on the surface would not necessarily qualify. The biosphere has repeatedly survived transformations that eliminated dominant groups and restructured ecosystems on a planetary scale. From the standpoint of the deep biosphere, many events that appear apocalyptic at the surface are disturbances rather than endings. The ultimate resilience of life arises from a simple fact. Biology does not care where energy comes from. Sunlight powers most familiar ecosystems, but it is not the only available source. Deep underground, microorganisms exploit chemical gradients generated by radioactive decay, water rock reactions, and geothermal processes. Near hydrothermal systems, life can flourish entirely independent of photosynthesis. As long as liquid water, usable chemistry, and a source of free energy remain available somewhere within the planet, biology retains a foothold. This is why the search for total sterilization becomes increasingly difficult the more closely it is examined. The target is not a species, an ecosystem, or even the surface biosphere. The target is every self-replicating system capable of exploiting any remaining energy gradient anywhere on Earth. A planet can lose its forests, oceans, atmosphere, and complex life long before it loses that final capability. The last chapter of life on Earth is therefore unlikely to be dramatic. It will be written by microorganisms inhabiting dark rock deep beneath a surface that has already become unrecognizable, persisting until even those final refuges are erased by changes in the planet's physical state. The scale of what would be lost. The biological value of what would be destroyed in a total sterilization event goes far beyond the organisms alive at the moment of the event. It encompasses the entire evolutionary heritage encoded in those organisms, the billions of years of adaptive experimentation that produced their molecular machinery, and the ecological relationships they form that constitute the functional architecture of the biosphere. Every organism alive today is the descendant of an unbroken chain of survivors extending back to the origin of life approximately 3.8 billion years ago. Every individual in every population carries in its genome the molecular record of every adaptive innovation that occurred in its lineage since that origin. The human genome, for example, contains +0 functional regions derived from retroviral insertions that occurred hundreds of millions of years ago. Gene families that trace to the first complex eukaryotes and core metabolic pathways that were already ancient when the first animal appeared. The genome is a palimpsest of evolutionary history, each layer preserving information about the environments and challenges faced by ancestors across geological time. The approximately 8.7 million named species on Earth, the 1 trillion estimated microbial species, and the unknown additional diversity in unexplored environments collectively represent a combinatorial space of genetic solutions to the problem of living in Earth's range of environments that is essentially incomprehensible in its magnitude. Each species is a unique experiment in biochemistry and ecology, encoding solutions to specific challenges that no other lineage has solved in precisely the same way. The genetic information encoded in Earth's biosphere is, by the calculations of information theorists, the largest naturally occurring information store in the observable neighborhood of the solar system. When an individual organism dies, This information is not immediately lost. It is preserved in the genomes of its relatives, in the shared sequences it holds in common with related organisms, and in the ecological role it plays that shapes the evolutionary trajectories of its interacting species. When a population goes extinct, more information is lost. The unique combinations of genetic variants that had evolved within that population, the specific behavioral and physiological adaptations to local conditions. When a species goes extinct, still more is lost. The unique evolutionary solution that species represented, irreplaceable except by convergent evolution over millions of years. In a total sterilization event, all of this information is destroyed simultaneously. Not just the organisms, but the information they encode, accumulated over 3.8 billion years of experimentation. The planet does not remember. The rock is chemically and physically changed by the sterilization event, but the genetic information has no physical substrate beyond the organisms themselves. When the organisms die, the information dies with them. There is no archive, there is no backup, there is no recovery of the specific solutions that 3.8 billion years of evolution produced, because those solutions exist only in the physical structures of the organisms themselves. If life were to re-originate on a sterilized Earth after the planet cooled and water returned, it would start from the simplest possible chemical beginnings, as it did originally. Whether the conditions for abiogenesis would be recreated exactly is uncertain. But if life did begin again, it would begin with no inherited information from the previous biosphere. Every step in the evolutionary process that previously required billions of years would have to be repeated. The second origin of life on Earth would have no relationship to the first. It would be, in the deepest biological sense, a new beginning on an old planet. The self-generated threat and why it matters most right now. All of the mechanisms discussed in this script, from the ocean vaporizing impact to the runaway greenhouse to vacuum decay, share a property that distinguishes them from the threats that deserve the most attention from any rational assessment of civilizational risk. They are outside human control. The cosmic threats operate on timescales and at energies that are not accessible to any technology humanity currently possesses, or is likely to possess in the near future. The asteroid that could trigger a runaway greenhouse, if one exists on a trajectory toward Earth, has been traveling on that trajectory for millions of years. The gamma-ray burst that could devastate the ozone layer will occur when the physics dictates, not when human policy permits. The self-generated threats are categorically different. Nuclear weapons exist because human decisions created them and maintain them. The nuclear arsenals pointed at populated centres worldwide could be reduced or eliminated by human decision. The atmospheric chemistry changes driven by greenhouse gas emissions respond to the scale of industrial activity, which is itself a product of human choices about energy systems. The biotechnology enabling the construction of dangerous pathogens is advancing along a trajectory that policy decisions could in principle constrain. The development of artificial intelligence systems capable of autonomous action on scales dangerous to human civilization is proceeding in ways that are at least partially responsive to governance choices. The self-generated threats sit at a peculiar intersection. They are less total in their potential impact than the cosmic threats, almost certainly not capable of total biosphere sterilization, but they are more immediate, more plausible within near-term timeframes, and more susceptible to human intervention. A Carrington-level solar storm will eventually happen regardless of what we do. A nuclear exchange depends on decisions made by identifiable human institutions. A pandemic caused by an engineered pathogen depends on technical capabilities that are advancing along a trajectory responsive to governance choices. The existential risk community's focus on these self-generated threats reflects a rational assessment of where human agency can make a difference. The nuclear winter scenario, which could potentially kill several billion people through the combination of blast casualties and subsequent famine, and which could reduce human civilization to a much simpler form for decades to centuries, does not rank alongside the ocean vaporizing impact in physical severity. But it ranks dramatically higher in practical urgency, because it is more likely to occur within any human planning horizon, because the decisions that could prevent it are made by identifiable actors whose choices we can attempt to influence, and because the gap between preventing it and failing to prevent it is the gap between human agency and human failure, rather than the gap between presence and absence of a cosmic event. The 2-hour frame that defines the fastest total extinction scenarios is in a sense a measure of how little warning time there is between the initiating event and the point of no return. For the ocean vaporizing impact, there is no reversal after the first 2 hours of surface temperature rise. For the gamma-ray burst, there is no preparation possible because the radiation arrives simultaneously with any possible warning. For vacuum decay, there is not even the 2 hours. The conversion is instantaneous at each location. Against these scenarios, the self-generated threats look almost manageable, not because they are trivial, but because they have precursors, warning signs, escalating indicators, and intervention points where human choices can change outcomes. A nuclear exchange does not happen without a sequence of political decisions, each of which creates opportunities for de-escalation. An engineered pandemic requires technical steps, each of which could in principle be detected and interdicted. A catastrophic climate trajectory includes decades of observable changes that signal the need for course correction. The appropriate human response to understanding the full range of extinction threats is therefore not despair, but a precise allocation of attention and resources. The cosmic threats deserve acknowledgement, monitoring, and where possible mitigation, such as the asteroid deflection program that represents genuine planetary defense against the lower end of the impact threat range. The self-generated threats deserve the primary focus of policy, governance, and institutional design, because they are the threats where human choices matter and where the gap between civilization-threatening outcomes and civilizational survival is bridged by exactly the kind of coordinated action that distinguishes complex societies from simpler ones, the ultimate extinction problem. The question of how all life on Earth could end in 2 hours has a precise physical answer, through the surface heating produced by an ocean vaporizing impact, which establishes globally lethal surface conditions within approximately 2 hours of the impact, and initiates a self-sustaining thermal feedback that will eventually sterilize even the deep biosphere on timescales of millions of years. The question also has answers from other mechanisms: vacuum decay delivering instantaneous conversion faster than 2 hours, gamma-ray burst delivering ozone depletion within minutes of arrival, each operating through different physics and each leaving different categories of survivors for different periods. What connects all of these mechanisms is the remarkable resilience they reveal about life itself. None of the mechanisms discussed here, with the sole exception of vacuum decay, which operates by changing the laws of physics rather than the conditions within them, can kill all life within 2 hours. The fastest of the natural thermal mechanisms requires millions of years to complete the sterilization of the deep biosphere, even when surface conditions become lethal within 2 hours of the triggering event. Life at the extremes of what is physically habitable is not merely an interesting curiosity. It is the reason the question of total sterilization requires the most extreme physical events to answer in the affirmative. The universe is not conspiring to end life on Earth. The cosmic mechanisms that could achieve total sterilization are genuinely rare. Earth has been habitable for 3.8 billion years and has survived everything the universe has delivered in that time. The empirical record is one of extraordinary persistence. Understanding the mechanisms that could theoretically overcome that persistence does not change the odds. It clarifies what those odds actually are and why they are structured the way they are. And it reveals that the threats most urgently deserving of human attention are not the ones that could end all life, but the ones that could end human civilization, and thereby remove the one new element that Earth's biosphere has produced in its 3.8 billion year history: the capacity to understand, anticipate, and potentially mitigate the threats that a universe indifferent to biology will eventually deliver.